course, no reason to say that to you. Okay, so what I want to do today is I want to talk a little bit more about some of the properties of the Fourier transform, Fourier analysis, Fourier series, and then this is going to be it for the Fourier transform chapter. Then we'll move to the benefit law chapter, chapter 9, where we'll start to use it. From there, we'll probably then move to, I think, chapter 12, Poissonian behavior. And so again, there's far too much stuff to do very quickly. I'm trying to concentrate on the key points. If there are things you want me to explain in greater detail, let me know. One of your homework problems was, I think, to prove Bessel's inequality. Right? So what did Bessel's inequality say? Good.
So f half of n squared
Good.
is less than the modulus of f, which is the inner product of f itself.
Okay, so we'll say the L2 norm squared, which is the integral from minus infinity. Well, we're doing 0 to 1, I guess. We're doing 0 to 1. 0 to 1 of f of x squared dx. So this gives you a relationship between the size of the Fourier coefficients and f. And there's lots of different ways to prove it. One of the questions is always, what do you want to assume about f? So what's a reasonable assumption? Yes?
It's square integrable.
So one is that it's square integrable, although what if it wasn't square integrable? Yeah, it's less than or equal to. So if it's not square integrable, no problem as well. Let's assume f is square integrable. Assume f is square integrable. So whenever you see something like this, one of the questions you could ask is, how different are the two sides? How much smaller could the sum of the Fourier coefficient squared be from the L2 norm? And in fact, we have the nice theorem. It is an equality for such f. So that's a very useful fact. We're only going to prove it if f is continuous. So proof when f is continuous. Why do I want to assume f is continuous? So a lot of times the functions we're interested in, the convergence is a lot nicer if f is continuous. If you take a course in measure theory, you basically learn to do a certain litany. I will prove something for simple linear combinations of step functions. And then from step functions, I get to continuous functions. And then from continuous functions, and you pass through this whole sequence of functions. And if you can prove it in one set, you often try to show that this set is dense in the other set that you care about. And so it turns out if we can do things for continuous functions, this is good enough for a lot of practical applications. If we're looking at step functions, the step functions aren't continuous, but we can tweak them ever so slightly, make them continuous without really changing things. So I'm going to just assume f is continuous, and you can try to do some kind of general limiting argument to get the other f. Or, as was remarked, in most of the cases we look at, f is going to be continuous anyway, so why not use f as continuous? Whose theorem or which theorems should you be immediately thinking about as soon as I say f is continuous? What does that give us? Fourier's theorem, and it also gives us Dirichlet's theorem. So Dirichlet's theorem is nice because we don't have to have the weighted coefficients. Fourier's theorem is nice in that it has a little bit better convergence. Okay, so we're going.
I thought we need differentiable for Dirichlet.
Oh, sorry, we do need differentiable for Dirichlet. I was just assuming additionally stuff that we need, but you're right. So since we're only assuming continuous, we can't use Dirichlet's theorem. We will have to stay with Fourier's theorem. Why might we want Dirichlet's theorem? Well, we're looking at something involving the sums of f hat of n. And sums of f hat of n, you're thinking the normal Fourier series. And so we're going to somehow want to compare the two. All right, so we start with the favorite inequality. If a is an R, then a squared is greater than or equal to 0. This is one of the most useful inequalities in all mathematics. And so in particular, what we would know is that the L2 norm of f minus Sn of f squared is greater than or equal to 0. And this is because we're just integrating the absolute value of f of x minus Sn f of x squared. And since we're integrating that, it can't be negative. So now, after doing some algebra, 0 less than or equal to f minus Sn of f squared. This is equal to the integral from 0 to 1 of f of x squared dx minus the sum, absolute value of n less than or equal to n, f hat of n squared. So that is just doing some algebra, okay? And you can see you're going to have a cross term. You're going to have, when you write what Sn of f is, you're going to have these exponentials coming in. You'll have like f hat of n times e to the 2 pi I nx. Well, f hat of n is a constant. When the e to the 2 pi I hits the f, that's going to give you another Fourier coefficient. Because of the orthogonality, we're only going to really care when we hit each other. Right. This immediately gives us, by correcting, the sum of n less than or equal to n of f hat of n squared is equal to the L2 norm of f, what I want, minus f minus Sn of f squared. Okay. Does this prove Bessel's inequality? So Bessel's inequality is just that the sum of the squares of the Fourier coefficients is bounded by the L2 norm. Yeah, because this is, I'm subtracting off something that's non-negative. So this proves Bessel's inequality. The proof now comes down to must show the limit as n goes to infinity of the L2 norm of f minus Sn of f squared equals 0. What would you love to use in here? So what would be wonderful to use here? Yeah.
Sn of f converges to f.
Yeah, I mean, if Sn of f converges to f, then eventually, let's say it converges uniformly. Eventually, it's always less than epsilon. I'm integrating over a region of length 1. This integral will then be at most epsilon. We win. That would be wonderful. Does the Fourier series always converge? So is Sn of f always going to converge to f pointwise? Unfortunately, no. If the function is in L2, it's a deep theorem that it converges almost everywhere. Well, that's enough to then finish the proof. This is the elephant gun nuclear bomb approach to mathematics, right? We should not have to use that deep of a result, right? All we need to know is we don't need to know that it converges pointwise. We just need to know that in L2, it's getting very close. All right. Now again, we could of course add additional restrictions to f. This is a wonderful restriction to add to f. So I wanted to use this earlier today and I couldn't. I was yelled at. What do I want to add? If f is differentiable everywhere, we're going to be twice differentiable to give myself a little cover, then that will be okay. But you kind of want to see what's the minimal conditions I need. Even assuming continuity is a little bit more than I really need to do, but I'm just trying to keep the main ideas of the proof transparent. So this is going to be very close to one of these 3 epsilon proofs. And so when we study this, the L2 norm of f minus Sn of f is equal to f minus, Tn f plus Tn of f minus Sn of f. So all we've done is we've added 0. This is an extremely common technique in analysis. Why do we do something like this? We offer f has nice convergence. T of f, the phase series, has nice convergence to f. Let's get that into the problem. How can we get that into the problem? Well, just put it in. Okay, you can't just put it in, so whatever you do, you have to undo. And now we can split this up. So this would then be less than equal to what?
Absolute value of f minus t and f.
Well, I have an absolute value. I have L2 norms.
L2 norms.
Yep. So f minus Tn of f L2 plus Tn of f minus Sn of f. Does everyone agree with that? That's basically a triangle inequality. So the only thing I have to be careful about is, what does this mean? I'm using this as shorthand notation. What this is really saying is the integral of f minus Sn squared versus the integral of f minus Tn of f plus Tn of f minus Sn of f squared. And I'm putting a square inside. So I'm basically saying a plus b squared is this equal to a squared plus b squared, where this is a and this is b. Is a plus b squared always less than equal to a squared plus b squared? I give you a counterexample.
A and b equal 1.
A plus 1. 1 plus 1 is 2. 4 is not less than 1 plus 1. All right, so that means we can't just use the triangle inequality carelessly over here. We have to be a little bit more careful. So a plus b squared is not less than or equal to a squared plus b squared in general. Is there any way to fix this? So when you have problems like this, you want to figure out what matters, what doesn't matter. I'm trying to show things go to 0. Let's imagine I could show this is true, but I multiply it by 1701. Now, this is going to tend to 0. This is going to tend to 0. If I multiply it by 1701, it still tends to 0. Is it harmful to multiply by 1701? What if I multiply by 24601? By 4135973 Okay. What if I multiply by log n? Does that matter?
It might.
It might. Depending on how rapidly this goes to 0, if I multiply by log, I think that's how many logs I had, and I can always go back and listen. Depending on how rapidly this goes to 0, if I multiply by a couple of log n, it will go to 0. So when I have something like this, I'm pretty sure this is going to go to 0. Let's face them. This has to go to 0. Come on. This suddenly probably go to 0. If I multiply by a constant, it will still go to 0. But I can't multiply by anything that depends on n without being afraid. And if I multiply by something that depends on n, then I'm going to have to really open up the analysis, which I want to avoid. So I want to give you a sense again. This is just 2 lines in the textbook. And I'm trying to decide what I want to talk about today. I really want to emphasize these 2 lines.
So multiply the right-hand side of that inequality by 2.
The right-hand side by 2. So one possibility is to multiply by 2. Are you convinced that a plus b squared is less equal to 2a squared plus 2b squared?
Well, the difference is 2ab.
Mm-hmm. So again, what you're trying to do is you're trying to be precise. You're trying to be like a surgeon trying to do the least possible thing. You don't want to hurt any of the tissue around. Nuke it. Give me a constant that you know will work. 2 will probably work. Is there anything else that would work? 3. Why would 3 work?
It's more than 2.
I have to learn twice today. It's wonderful. But can you prove that 3 trivially works? There's a constant where I can trivially prove it works. The first one that I can trivially prove works is 4.
Yeah.
So why is it trivially true if I put in a 4?
Because that's 2a squared plus 2b squared.
So it's 2a squared plus 2b. Well, okay, so I have a squared plus b squared plus 2ab. If you want to look at it, what I want to do now, let's say b is larger than a. And this quantity here is at most b plus b, it's at most 2b, it's at most 4b squared. So if I put in a factor 4, I'm safe. And it's not going to affect any of the proof later. This is the mindset of the analyst. It's not going to affect anything, so put in the easiest constant you can work with. So I can just put in 4s here. Now the interesting question becomes, what is the smallest constant I can put in? Okay, yes?
Do we have to worry if things are getting really small and we're adding a squares and b squares, that then that'll be much smaller than just a, b? Or no?
Well, just look at the left-hand side. If I want to make it as large as possible, I can replace a plus b with the maximum of ab plus the maximum of ab.
Right.
The largest this is when a equals b. And then here, again, this is of course ridiculous overkill. If a equals b, this could be 4a squared, but 2a squared plus 2b squared would also be 4b squared. So I don't really need something as large as 4. A really good question is, what is the smallest constant you can put in? Do you think you can get by with a constant less than 2? Anyway, we can answer the question, how far down can you go? Really, trivially low down for how far down you can go. You can't go smaller than what?
I'm thinking you can go smaller than 2.
I don't want to go smaller than 2, but it requires thinking. I don't want to think too much. A constant I definitely can't go below.
You can't go smaller than 2 because in our example it's just a 1 and 1.
Okay.
It's a 2. It's if you went smaller than that.
Oh, so we're using an example to show we can't go lower than 2. All right. Unfortunately, I forgot the example because that was so long ago. Trivially, what constant can't I go lower than? 1. If I've got a squared plus b squared over here. Clearly, I've got to have a constant at least 1. I've got a constant at most 4. So it's somewhere in the range from 1 to 4. Is this really worth arguing over? Is this really worth spending time over? Well, if the answer is no, you're going to waste your time today. Okay, it's not worth spending time over in terms of trying to do any of these proofs. It's worth spending time over in terms of trying to think like an analyst. This is how they think. So just replace it with a 4. Okay, now that we've replaced it with a 4, now we can move on. Okay? So again, major point. Now we finish the analysis. This goes to 0 by Fourier's theorem. So in particular, what this means is, given an epsilon, we can choose n naught such that for all n greater than or equal to n naught, this is at most epsilon over 2. Or epsilon over 8. Okay? There's a huge analysis community as to, do you arrange all of your stuff so that at the end of the day, you prove something is less than epsilon, or you prove it's less than a multiple of epsilon? If you're trying to impress people, you have it all set up so that it ends less than epsilon. Does it really matter? If I say it's less than 5 epsilon, is that equivalent? Yes. But a lot of times people will do epsilon over thirds, epsilon halves, so you can say there exists an n naught such that for all n greater than or equal to n naught, it is less than or equal to, let's do epsilon over 8. Cameron was doing his homework last night, and he had to put 15 words into different boxes. And he decided he wanted to not just put them in the order in which you're going down the list, but in alphabetical order within the boxes. I was happy to see him taking that extra effort. Doesn't really matter, but same principle here. At the end of the day, I will have it strictly less than epsilon, not less than epsilon times 2 or something like that. I'm now left with a more interesting piece. Now we're left with the Tn of f minus Sn of f. We want to make sure that this gets small. So we have to study Tn of f minus Sn of f equal to 1. So this is the integral from 0 to 1 of Tn f of x minus SNF of x squared dx. All right. If you think about what's going on, what's the difference between Tn and Sn? So what's the difference between Tn and Sn? Weights. So when I subtract this, I'm basically changing, I have the weights over here. These give me the weights like 1 minus the absolute value of n over n. I then subtract the 1, I square things, and after I do all the algebra, just to save some time, we end up getting that it equals the sum of n less than n absolute value, n squared over big N squared, f hat of n squared. Okay, so this is just algebra. And it makes sense that we should have something like this. If we think about what's going on, what's really nice when we have a complex function we're integrating a square is we write it times its complex conjugate. So we'll have e's to the 2 pi I nx, and we'll have e's to the 2 pi I nx complex conjugate. The complex conjugate of an exponential is the sum of a negative. We replace I with minus I. So when you look at what happens, you're going to have an e to the 2 pi I nx, you'll have an e to the negative 2 pi I nx. The only term that will not go to 0 when you integrate is when n equals m, and that's why we're going to get reinforcement, that's why we're going to get squares here. Okay, so again, this is not doing the algebra. You should do the algebra. I should not do algebra in public. Okay, but this gives you an idea of why this is what you should expect. Because when we have modulus squared, the only things that survive is the reinforcement, and it's a beautiful way of writing the complex conjugate. This will be very important when we get to the circle method. We want to study the sum. Okay? And we want to study the sum when n is large. So when you have a sum like this, you can break it up into different regimes. So you have when n is small and when n is large. When n is small, what do we know? What can you say about contributions? When n is small. It's small because n squared over big N squared. Well, now f hat of n squared is bounded. So when n is small, the contributions are going to be negligible. Now the problem is, what if we have a lot of small n's? So if you've ever, how many of you have read Gulliver's Travels or seen or heard about it? You have the Lilliputians attacking Gulliver. Is one Lilliputian going to be able to foil Gulliver? No. What about 2? What about 1 million? Enough little guys will take down the giant. Okay? That's what's going on here. If I have 2 little n's, the contribution can become large when I sum over them. So I need to break things up so that the contribution from the little n's is small when I sum over all of them. Okay? This is the whole idea, is you need to introduce some kind of parameter. I'm going to break this up into a sum. Absolute value of n is this equal to n to the delta n squared over big N squared, and this is going to be bounded universally by some constant b squared. Plus a sum, the absolute value of n is greater than or equal to, and is strictly greater than n to the delta of n squared over n squared f hat of n squared. So there's a lot of really good ideas in the analysis here, and this is why I want to go through this proof very carefully. This is thinking like an analyst. We know that this is bounded, so I'm going to put in the bound here. I'm breaking it up. I don't know okay, I do know that I've done this many times in my life. I'm going to pretend I don't know why I should break it up, so I'm going to just put in some arbitrary parameter delta, and I've got to figure out how I want to split it. And now I have 2 things. Well, when I look at the contribution from this piece is going to be a row. It's going to be b squared, and then this will be at most, the largest value we're going to have is, I think, n to the delta. Right? So the number of terms I have is I have n to the delta. Okay, well, yeah. This is another terms do I have here? Plus 1, right? It's a little annoying. So I'm going to subtract 1 over here, and I'll put the delta equal to there. Now I have n2 into the delta minus 2 plus 1, so I can now bind that by just 2 into the delta, and I don't have to worry about all that little annoyance. Okay, doesn't really matter, it'll make it a little bit cleaner. So it's less equal to b times 2n to the delta. How large is each piece there? Each piece is at most n to the delta. And so one possibility is I could put an n to the 2 delta, and I divide by n squared. And then over here, I'm actually going to just sum over all n greater than equal to n to the delta. Actually, my sum only goes up to big N over here. I'm going to drop this fraction and just put in f hat of n squared. Why is it okay to drop this fraction?
Getting close to 1.
It's getting close to 1. Okay? So, again, I'm being extremely wasteful here. I want to really teach you how to be wasteful in a good way. Okay, don't talk to the Civic Center people here. All right? Could I have done better? Yeah, but when it's literally as large, n squared, or big N squared, is essentially 1. So as literally it's very large, this is really not that harmful. What about over here? Was it harmful in replacing log n squared with n to the delta, n to the 2 delta? Could I have done a little bit better? And so I've got this whole expression as n to the 3 delta. What if I just summed n squared directly? Well, if I summed n squared directly, I get n cubed over 3. I put in n to the delta, and I get basically n to the 3 delta over 3. So the net effect of all of this is instead of having a 1/3, I've got a 2. I change by a factor of 6. And it makes it a lot easier. I don't have to use the formula for sums of squares. And again, I'm not trying to win by a constant. Things are not that delicate. All that matters is the behavior of the independence. Yes?
Should that be b squared then?
Yes, it should be b squared. So again, I could have done a slightly better estimate here. It's not going to help. So what can you tell me about delta? How large can I take delta? So if I take delta to be a half, then I will get n to the 1/2 times n to the 1 is n to the 3/2 over n squared. If I take delta to be 1/2, I'm fine. Could I take delta to be larger than a half? Yeah, because I know n to the 3/2. I can take delta to be a little bit larger. As long as 3 delta is less than 2, so as long as delta is less than 2/3, I'm okay. Any delta less than 2/3 will win. Okay, so just need delta less than 2/3. Example, delta equals 1/2. So if I do that, that's going to be more than enough to guarantee that this term is small. It turns out for this term, I don't really care that much. Yes?
Could you have used log n?
For over here?
Yeah.
Yes. In fact, I could probably get that with anything that goes to infinity with n. Log n would have worked. Frequently in problems like this, you often try to balance the two different sides so that their growth or their decay is similar to try to get the optimal rates. Right now, I'm not trying to get optimal rates, but those are good things to have in mind for future, so it's an excellent point. Over here now, what do I know about this sum? I'm summing all the absolute value being greater or equal to n to the delta. In fact, I'm extending it all the way up to infinity. I don't know if you noticed. I don't like the big N anymore. So I'm going to add it up to infinity. Is that okay? Why can I get that with extending it to infinity?
Because the limit of the f hat ends with 0.
Right. But that doesn't necessarily mean it converges. Do you know that this sum converges?
That's what we're trying to find out.
No. No, the sum converges. We're trying to show that the sum equals the L2 of f. Remember, Bessel's inequality. Bessel's inequality says that this sum over all n converges. So if it converges, then the tail has to go to 0. So Bessel's inequality there exists an n naught tilde such that for all n greater or equal to n naught tilde, this is at most epsilon over 10. Right? So this is just Bessel's inequality. Bessel's inequality tells me this sum converges. So I can choose n sufficiently large so that this is at most epsilon over 10. And then all I have to do is go back over here and just choose a value of n so that if n is sufficiently large, this is also at most epsilon over 10. And then I'll have epsilon over 8 plus epsilon over 10 plus epsilon over 10. Clearly that'll be less than epsilon. Yes?
So we start, at what point do we prove Bessel's inequality?
We prove Bessel's inequality very early on. At this point over here, this gave us Bessel's inequality. Right? Because once we're at this point, yeah. All right, so I'm going to have to walk over because of the way this is recording. Come on, there you go. So over here, we're trying to prove Bessel's equality. At this point, we have Bessel's inequality. The sum.
Okay. Yeah.
Well, technically, I need to do one other step to make this Bessel's inequality. This is true for all big N, sum big N to infinity.
Okay. I see.
So at this point, we have Bessel's inequality. We can use that as a homework problem. This is the simplest way to prove Bessel's inequality.
Okay.
And we're refining Bessel's inequality to an equality. And we split it up into different parts. So again, this is one of the best examples I know of proof by standard analytic thinking. We keep breaking things up into parts we understand. We make each part small, and we don't obsess over the values because they don't matter. It doesn't really matter if this is a 4 or a 2. Okay? And if each one of those are various tricks, we put in this because we can only use Fay's theorem. Over here, when we attack this, we have the weighted sum, we expand everything out, and when we do that, we split it up into different pieces, and now we split the sum, and we're trying to take advantage that this is in a tail. Okay. Any questions about this? So again, a lot of great ideas in this proof. A lot of ideas that you can use for a lot of other problems. It doesn't matter, at the end of the day, we have an equality. Does it really matter how we are splitting on these things? No. Because at the end of the day, we have Bessel's equality. So in fact, it really would help us to try to optimize the other terms. It's not needed. So it's really good to get a sense of what matters and what doesn't matter in problems like this. All right, there's lots of applications of this. I'm not going to go through it, but in the book, one of the examples is to use Bessel's equality law to actually evaluate certain series. So if you want to sum 1 over n squared, here's a way to do it. So if you're going to be a math major, you need to know the sum of 1 over n squared is pi squared over 6. And we'll see later in the semester that this proves there's infinitely many primes. But one way to evaluate this and see that it's pi squared over 6 is to find a function whose Fourier transform, f hat of n, is like 1 over n. And when you square things, you get 1 over n squared. Or you're not going to find something that's exactly like that. You might have to find something that's close and play some simple shifting games. Okay. Any questions on this? Okay. So as you can tell, there was a lot of stuff in here that I liked. We broke things up into 3 parts. We used different techniques in each one. We showed each part was small. This is a standard 3 epsilon proof. And so it's often called that because at the end of the day, people are lazy and they don't show it's less than epsilon, they show it's less than 3 epsilon. And we have each one of these terms is less than epsilon. Okay. So in the remaining time for today, I'm going to talk a little bit about Poisson summation. And so Poisson summation is one of the most important tools we have. And one of the questions in this is always, what class of functions are we going to work with? And so I want to introduce you to the Schwartz space. This is one of the two, I think I spelled it before. So S of R is all functions f such that f in all derivatives decay faster than any polynomial. So for example, I look at the kth derivative of f, and this will be less than equal to some constant over x to the m plus 1 for any m. So it's decaying fast. Now, that is correct, but I want to write minus c like this. What should I really write for the c?
C of x?
Not c of x. C does not depend on x. What does c depend on? It depends on k. Anything else? On m. Now this closes your papers. And so I'm going to just write c, but it's not bad to write that it depends on both k and m. Why do I have the plus 1 down there? I mean, if x is large, the plus 1 doesn't really matter. Why do we have a plus 1? Yeah, if I take x equals 0, it's still not a true statement. Is it true when I put in x equals 0 if I don't have the plus 1? No. Is it useful? No. So I want to have some control over what's happening to my function as 0. If I don't have the plus 1, now I imagine this is giving me very useful information. All right. Then I have the Fourier transform. So f hat of y is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. There's not enough time to go into all the great stuff you can say about the Fourier transform. There are times when you can recover f from knowing f hat. So the way you should look at it is the Fourier transform, you give it a function, it gives you a new function back. Well, in the case, well, if I give you the Fourier transform, do you know the original function? However, there are multiple functions that can have the same Fourier transform. Is there a uniqueness? Well, which space of functions does the Fourier transform behave nicely? The Schwartz space behaves very nicely. So some of this stuff is discussed in the book. For those of you who do physics or differential equations, lots of applications there. The Fourier transform has wonderful interactions with multiplication and differentiation. And there's some exercises about that that's worth reading just to get on your radar screen. So one other piece of notation, we say a function decays like x to the minus a if there exists an x naught and a c such that for all x greater than equal to x naught, the absolute value of f of x is less than equal to c x to the minus a. So this just tells us a little bit about how fast our function is decaying. What do you think would be good values of a to take? How large do you want a to be? What would be a good value of a that we would love to have? Yes? 2. Why 2? The integral will converge. In fact, you can get better than 2 as long as it's greater than. So as long as it's greater than 1, the integral will converge. Okay. That's a very nice property. And so Poisson summation is the following. Poisson summation. Assume f prime, f double prime, decay like x to the negative 1 plus eta for some eta greater than 0. Then the sum over Ln of f of n, I'll do it this way, is equal to the sum over Ln of f hat of n. So this is a wonderful relationship. It basically tells us that summing a function of all the integers is the same as summing the Fourier transform of all the integers. Now the proof is f of 0 is f hat of 0, f of 1 is f hat of 1, f of 2 is f hat of 2. No. They take on a lot of different values, but somehow when you put them all together, it works out. What makes Poisson summation so useful is typically what it does is if f is slowly decaying, f hat is rapidly decaying. So f slowly decaying, f hat rapidly decaying. If f is slowly decaying, if I want to understand the sum, I have to take a lot of different terms. I have to have a long sum. So I have a long sum of slowly decaying things. If f hat is rapidly decaying, I have a short sum of small things. That's much better. And in fact, what often happens in applications is you only need to take one term on the right-hand side to approximate the sum very well. You typically just need to take n equals 0, and anyone who's working on Benefit's law knows that essentially n equals 0 gives you almost the entire sum. And you don't know how much you're off by. So this is a wonderful trade-off. You replace a long sum with many terms with a short sum over a small number of terms. Okay, so the question is, how do we prove something like this? Well, since this is the chapter of Fourier analysis, maybe we would, not surprisingly, use the different techniques we've done. We haven't done anything on the unit interval. So the question is, can we somehow convert this to a problem where we can use our results? So for example, we're looking at an interval 0, 1, but now I have a function that's defined on R of R. And the Fourier transform is on R of R. So I need to somehow get a periodic function. So I need a periodic function on 0, 1. And if I have a periodic function on 0, 1, then I can use all the results we've proved. So this suggests that we define f of x to be the sum, n goes from minus infinity to infinity, of f of x plus n. Is this periodic? Does f of x equal f of x plus b for some fixed b? And if so, what would that b be? What's the period of this function? So it's periodic with period what? With period 1. If I replace x with x plus 1, I get f of x plus 1 plus n. Well, 1 plus n also ranges over all the integers. So this is a periodic function. The problem is it doesn't always exist. So does not exist for all f and x. And so there's an example in the book of looking at a spike which shows you the trouble that can happen. Can anybody give me some conditions that you think will imply that this function exists? Any conditions on little f that should imply that this function exists and is continuous? Yeah. Probably that's why over here I'm saying Poisson summation. Assume f prime, f double prime decay like this. There might be more than we need. It might be a little bit of an overkill. I don't care. These conditions are very weak. They're meant in practice. So if f decays enough and derivative 2, we're okay. And those are the conditions we've been talking about. And then I go through the analysis in the book about why this is enough to show that this function exists and is continuous. So we get big F exists and is continuous. Ooh, we have a continuous periodic function on 0, 1. What are you thinking about? So what's your first thought? We don't have much time. You've got to think fast. What are you thinking of? We've got a continuous periodic function on 0, 1. Phase theorem. All right, so we want maybe a little bit more, and it's continuous. And differentiable, too. All right, now what are you thinking? Now we're thinking Dirichlet. And so we can get f of x will be the sum f hat of m e to the 2 pi I mx. M goes from minus infinity to infinity. And these big F's are going to be the Fourier coefficients of my function viewed as a function on 0, 1. What would be a really nice value of x to take? Zero. So if we look at big F of 0, we have a sum, m goes from minus infinity to infinity, of f hat of m. And if we take 0, we get a sum of f of n. N goes from minus infinity to infinity. Hey, that's almost what we want. All we need to do is show big F hat of m equals little f Fourier transform of m. And then we're done. And this comes from unwinding things. So big F hat of m is the integral from minus infinity, no, the integral from 0 to 1 of big F of x e to the negative 2 pi I mx dx. And this is the integral from 0 to 1 of the sum, and it goes from minus infinity to infinity, f of x plus n e to the negative 2 pi I mx dx. What do you want to do now? So what do you want to do? I have an integral of a sum. Switch them. So I'll send you a video of Cameron teaching you how to switch orders of summation and integration. You switch them. You've got to be able to justify this. It turns out if you put in absolute values, if it integrates to something finite, you're OK. You put in absolute values, you're fine. And now what's going to happen is you have this integral from 0 to 1. You have the sum over n that's going to extend it to be an integral over all of r. And that'll get you the f hat. So I'm going to leave the rest of the algebra details to the book. I will not go into the central limit theorem in class. I know some of you have seen it with me in probability a few years ago. It's just a good thing to read about if you're interested. This gives you a great sense of things we can do. All right, so on Monday, I'll send you an email on what to read. We will now turn and apply this stuff to Benford's law. And so I'll tell you later this weekend what you should be reading from chapter 9.